Hi, Bisky and Morgan and Callie and anyone else. All right. Okay. You were supposed to, over the weekend, label this thing. Oh, yeah. How many of you did that? What? Shocker. Okay. I will pause this for a couple minutes while you finish writing. It's okay. So the most important thing you need to know here is the direction of the electrons. You can see the electron is written right here, and it's flowing from the anode towards the cathode, which makes sense because we learned red cat. You tell your lab partner real fast what red cat meant. Definitely not. So reduction is at the cathode, and what does reduction really even mean? All right, you gain electrons. So are we ready? We're taking zinc. Zinc is being oxidized because it lost an electron. That electron had to go somewhere. It travels to copper, which is reduced, so it gains an electron. Now, there's some complicated things right here. This thing is called a salt bridge. And it's not always a tube with an electrolyte in it. A lot of times it's just like a piece of paper that's wet, like it has a salt on it. That's how a battery, it's just a cardboard thing that's wet. And a lot of times your battery, when it gets old and dies, it's because that piece dried out. So the salt bridge is necessary because if I take an electron and I move it from here to here, all of a sudden there's an imbalance in charge. Even one single electron now, this side becomes negative and that side becomes positive. Well, will another electron flow towards this if it's already negative? No, it would stop. So what happens is the electrons travel here, and then the salt bridge provides the opportunity for charge to be distributed. So as this happens, the NO3 ion will migrate towards the anode, and the Na plus ion will migrate towards the cathode. And that's because Na plus wants to be where it's negative, and NO3 minus, it's right there, it wants to be where it's becoming positive. So you kind of all right with that? If we remove this salt bridge, tell your lab partner what will happen. Should I look at this then? Are we ready? So once again, since I forgot to hit record, the cathode will take the copper 2 ion and convert it to copper metal, which sticks to the cathode, so it gains mass. The anode will lose mass because the zinc solid becomes the zinc ion in solution. So the concentration of the solution of Zn plus 2 goes up here. The concentration of Cu plus 2 goes down over here. You okay with that? All right, let's look at the next slide here. So this will explain the reason for a salt bridge. Once even one electron flows from the anode to the cathode, the charges in each beaker would not be balanced and the flow of electrons would stop. All right, therefore we use a salt bridge, usually a U-shaped tube that contains a salt solution to keep the charges balanced. Cat ions move towards the cathode. That should be easy to remember. And anions move towards the anode. Let me move this. Are they? Oh my, why is this so hard to move today? Hello, Lisa. It's been forever. Okay, are we all right with these? Do you need me to pause? You writing anything down? You should have had these arrows labeled at the bottom anyway. Okay, in the cell then, electrons leave the anode and flow through the wire to the cathode. As the electrons leave the anode, the cations form, dissolve into the solution in the anode department. This is everything we said. Okay, next. As the electrons, oh, whoa, did I go too fast? Oh my. All right, as the electron reaches the cathode, cations in the cathode are attracted to the now negative cathode. The electrons are taken by the cation and the neutral metal is deposited on the cathode. So that is why it's gaining mass. Are you writing? You don't have to. All right. Electromotive force. Before we move on to that, I want you to turn to a completely new page. And I want you to see if you can, I want you to see how much you can already label. Because you need to label these very well. So we'll just switch things around. We'll call this the cathode. We'll call this the anode. Oh, there's our salt tube. And we use the same thing. We're going to have zinc, we're going to have copper, we're going to have NO3. Okay, will you label as much as you possibly can from memory? Okay, so first thing first, where does the electron flow from and to? Where's my arrow? Left to right, right to left? It's going from the anode to the cathode. I wrote this backwards than the one that was in your notes. Okay. What's that? I am. So I'm going to put an arrow one way and an arrow this way. Which way does the anion flow? Towards the anode. So we have anion on top, right? That means cation down here. Good so far? All right. So you'll learn a way to know this, but copper was our same cathode, right? And zinc. And so I didn't give you, well, I gave you NO3. So NO3 is going where? All right, it's okay. It's going this way. And then I guess in the example, was it sodium nitrate? Was Na plus the other thing? Okay, I didn't put that. But Na plus, it would be heading this way, right? Okay. The only last thing that they might ask is for you to label where reduction and oxidation happens. So we would have reduction here, right? And oxidation here. If you can label every part of that we just put, then you'll get 100% on the test, or you would be fine on any AP test. Okay? It's very typical, if they have a question here, it will ask you to explain the purpose of the salt bridge, and the simple answer there is to balance out charge. As an electron flows from one place to the other, you have to have something that can balance that charge out, and that's what we use the salt bridge for. Okay, now make sure you can do this. Like write it 10, 20 times, whatever you need to do to commit this to memory. This should be automatic. It should be something that's in the free response that you like pray is on there, because it's not brain power, it's barf power. If you can memorize it and just upchuck it onto a piece of paper, all right, it's nice. There's not very many, but they do love you to draw things. This is, I'd say you have a 33% chance every year that you have to draw one of these on the AP free response. All right, now, electromotive force. So the electromotive force is, we're going to talk about why this electron will move one way or the other. All right, so literally electromotive, meaning what's the motivation for the electron to move, or what's the force that's going to push it. All right, so here we go. Water only flows spontaneously in one way. Likewise, electrons only spontaneously flow one way in a redox reaction from higher to lower potential energy. Okay, so that's all they're doing. They're trying to get to a more peaceful place in their lives, essentially. So the cathode is always the place with lower potential energy, because the electron ends there. All right? Exactly the same thing like a waterfall. The potential difference between the anode and cathode in a cell is called the electromotive force. It is also called cell potential and is designated E cell. Now, it's not this right here. It is, well, it's right there. The cell is lowercase. We're going to measure this in voltage. Okay, so I drew these two lines over here. If we were talking about water flowing over a waterfall, if these two were at the same height, would the water flow? Not at all, right? And neither would the electrons. This EMF essentially is, in fall speak, it would be how far it is from where the water started to where it fell. And that's easy. Like the farther it is, the harder the water would hit you down here, right? In cell potential, we're going to measure the voltage of each of these cells, and the difference between them will tell us the flow, or the voltage, or the electromotive force, the reason why the electron will move. Now, one thing, and it will probably say it, the voltage, or EMF here, is dependent on how far it falls, not how many things fall. Like the energy of a waterfall is dictated by E equals mgh. It's essentially times gravity times height. And I know it has mass, but we're talking about each individual electron. Or in a waterfall, we'll talk about each individual water particle. It doesn't matter how many flow over them. It just matters how far they fall. All right, cell potential is measured in volts. 1 volt is 1 joule per coulomb. Now, does anyone remember what a joule is? We've used it. It's energy, right? Does anyone remember what a coulomb is? It's a measure of charge. So volt relates energy and charge, and the movement, essentially, of that charge and how much energy it took. All right. So, this thing is from the AP test. You are given these. It's called reduction half reaction cell potentials. And it will just be a gigantic list of stuff. And that's great. You'll only use like one, or sometimes you'll use 0 of these, but it's given to you every time. These are the values of the distance, essentially, between the top and the bottom. You okay with that? So we have fluorine plus 2 electrons goes to 2F minus. Does fluorine want to gain electrons? Absolutely. It's the most electronegative thing ever, so it has the most positive cell potential. Okay, coming down here, does lithium want to gain an electron? No. So it has the most negative electron potential. So if we could make a battery between lithium and fluoride, we'd have a dang impressive battery, right? Now, we don't have those, but we do have batteries we call lithium-ion batteries. Well, why do you think they chose lithium? Because it is such an awesome loser. It wants to give electrons very much, very easily. So we make these batteries. We use lithium ions. We pair them with one of the things higher on the list, and you can get a lot of voltage out of a pretty small atom. All right. Now, we'll talk a lot more about this. Because fluorine and fluoride is a very, very dangerous chemical. It's extremely toxic to us. Like if you come across a piece of lithium and touch it, uh-oh. I'm getting a red beep. You'll live. If you come across any fluorine or just raw fluoride, you'd be in a lot of hurt. So they're just dangerous. I don't know why this is red. I've never had it do that before. Maybe the thing I'm plugging it into isn't plugged in. Anyone ever charge something into a cord that's not plugged in? Oh, it is. Oh, well. Okay. Feel like something's wrong. Anybody else think something's wrong? Okay. Okay, hopefully it all works now. So the cell potential at standard conditions can be found through this equation. This equation is extremely important. It's the most likely thing you'll be tested on in this entire chapter. So the energy of the cell is equal to the E naught for reduction, which is the cathode, minus E red at the anode. Now, this is sort of tricky because we know reduction happens at the cathode, but does reduction happen at the anode? No, but we're going to use the same value and the math will work out just fine. All right, because cell potential is based on the potential energy per unit of charge, it is an intensive property. What does intensive property mean anymore? Nobody? What is an intensive property? It's been decades since we went over that, right? That was chapter 1 or 2. Like, yeah, go ahead. It's way early in your notes. Now, this goes back to our picture before. So it says for the oxidation in this cell, I don't know if I love this slide, but whatever. You have these two values that can be found in the table. So we know zinc was oxidized. We know copper is reduced. We should know that based on what we saw and where they were. Are you okay with that? So you would find these data tables, you would find these values in data tables. Okay, next. All right, there's a lot of stuff here. So we then plug these values in to this equation. We take what was happening at the cathode, and then we subtract what was happening at the anode from it. All right, we keep the same signs as we found, and make sure that you subtract. So most of the time you'll have a minus, so you really have a plus. Does that make sense? Okay. We want this value to be positive or it wouldn't happen. Okay. I can't guarantee this will clear things up, help or hurt you, but I'm going to read it anyway. So note, and this comes out of the study guide, if I remember right. So there's your reaction or your equation. It says both potentials used in this equation are standard reduction potentials, which are typically what you find in tables. However, the reaction of the anode is actually an oxidation reaction, or the reverse of a reduction reaction. This explains the minus sign. We would have used a plus sign had we been given an oxidation potential, because they could give you that, and that's super annoying, but that could happen. The subscript of 0 in E0 indicates that these potentials are correct only when concentrations are 1 molar and pressures are 1 bar or 1 atm. The correction called the Nernst equation must be applied if conditions are different, and that's no longer tested, so we do not worry about it. But what you're going to do, you'll find these numbers, you'll plug them in, and that's why you're going to, answer's right there. That's why we have our minus instead of adding. So calculate the standard potential of the following using Appendix E. Easy. Do you know why it should be easy? Okay, because H is called the standard or electron potential. It's always 0. So really you just had to have F, and it was what number? 2.87. Positive or negative? Positive. So fluorine should lose oh, wow, that went fast. Okay, what did you get for this one? 3.2? It was 2.91 and 3.33 something. Positive or negative? Positive. Okay, we'll pick more of this up tomorrow.